अच्छा ये क्या कि first question. अच्छा, the first question is benzene undergoes nitration. ठीक है, so it's किसकी बात हो रही है? That's nitration of benzene. So it's basically, let's open the notes. के कहाँ पे? Where did we discuss nitration of benzene? Let's hold on one second. So nitration of benzene is somewhere at the start. So the first question is about benzene's nitration. एक सेकंड है ना, ये लोड हो जाए. ठीक है. So that's basically benzene, and the nitration of benzene is this thing happening. That in nitration, what happens is, in all substitution reactions, this is what happens: that there's a benzene, and in this case, it's Br positive that's coming in, but it could be an NO2 plus when there are two nitrations. There are two electrophilic substitution reactions. One is bromination, the other one is nitration. So we did nitration as well. That in nitration, what happens is that you pretty much have the same reaction, except that it's an NO2 plus one that's coming in. So imagine karo कि it's the same reaction, but instead you have NO2 plus one. So instead of Br, you have NO2 plus one. That's what you should imagine. So if you go back to the question, he states the shape geometry around the substituted carbon atoms in the benzene molecule. So benzene में the carbon is, the first one is benzene. He's talking about benzene. In benzene, the carbon is sp2 hybridized. So this is what you're going to write. Okay, the shape and geometry, it's talking about the shape and geometry. So it's trigonal planar. Not sure if he's asking for the angle, lekin that's trigonal planar. I mean, we can write the angle, we can write the hybridization as well. We can call it sp2. The carbon is sp2 hybridized. बस मैं वो ट्राई करता हूँ. मुझे मैसेज पे ना एकदम फिर रिमाइंड करा देना, ठीक है? मैं वो शीट भी शेयर कर दूंगा. चलो मैं करता हूँ उस पे. अच्छा, intermediate complex. What's the intermediate complex? So the intermediate complex is going to be this one. That the NO2 is going to come in and it's going to steal one of the carbons. So I wrote that carbon becomes, for a temporary instant, as an intermediate, the carbon is now making 4 bonds. So the geometry and the shape, when it's making 4 bonds, that's tetrahedral, it's sp3 hybridized. So instead of being sp2 hybridized, once it starts making the 4th bond, it now becomes sp. So intermediate complex, it's sp3 hybridized, and again, he's talking about the shape and the geometry. So that's tetrahedral. And the angle is going to be 109.5 degrees. And then in the nitrobenzene product, once the substitution has taken place, what happens finally? Finally, what happens is that the H leaves and the benzene pi electron cloud is reformed. So the geometry is again sp2 hybridized. It's again 120 degrees. So it comes back to the original geometry. So that's again the same old one, right? Clear? Munia, is this clear? It's again sp2.
सर आप ये intermediate explain कर सकते हैं दोबारा?
मैं explain करता हूँ. Just one second. Where's there is? So it's again sp2. It's again trigonal planar. And it's going to be 120 degrees again. Achha, the intermediate, explaining the intermediate again once more. What we did was electrophilic substitution, that you had benzene, right? How was benzene formed? If this opens up. So benzene originally had a carbon that was sp2 hybridized, making 3 bonds, and there was a 4th electron. Each of the carbon atoms was exactly the same, and they would overlap and they would form this pi electron cloud. Okay, Ibrahim, you clear? Do you have a pi electron cloud? Is that clear?
जी, yes sir.
So then what happened was that electrophilic substitution. What is electrophilic substitution? Just 1 second. Let me just open 2 other files. I mean, this thing lags a lot. Just 1 second. Where's no, this is AS, sorry. I said this one. This one has electrophilic substitution. Just 1 second. Yeah, that's still stuck. So coming back to this, this was electrophilic substitution. Let me just quickly explain what electrophilic substitution was. That that this is benzene structure, right? And what would happen is that an electrophile, like in this case, it's Br positive. Carbon is making, like if you focus on the carbon atom, it's making 3 normal bonds and there's a 4th electron that's delocalized, right? So when the positive bromine comes in, it steals that 1 p orbital. Ibrar, is this clear? This is positive. So what happens is that one of the carbon atom is no longer sp2 hybridized because it's now making 4 bonds. It's the 4th electron that it had, a spare electron, that is now bonding with bromine. Right? Is this clear? So all the other ones have this spare electron, so they have delocalized electron clouds, but not this carbon atom. Is that clear?
Yes, sir.
And the next thing that happens is that the benzene electron cloud is short of 1 electron because bromine took its electron. So it's got a positive charge now, so it wants that electron back. So the way it can get that electron back is if the H gives the electron back. So the H decides to give the electron back, so the p orbital is back again. The H leaves, it leaves and bonds with HBr, Br minus 1 from which had previously left. I mean, you had a Br minus 1 that had previously dissociated. So the H leaves, gives the electron back, the benzene electron cloud becomes complete again. But in the process, one of the H is gone, and instead in its place, you've got a bromine. Okay. Now, nitration would be exactly the same. Like if you look at nitration would be exactly the same. This is the entire mechanism that's drawn over here. The Na2 plus 1 comes in, takes away one of the p orbitals, bonds with the carbon atom, and in the next step, the H leaves. The catalyst is H2SO4. The HSO4 minus 1 attracts the H leaves the electron back. The benzene electron cloud becomes complete again. TK, is that clear? The whole process. And that's the mechanism that you're going to draw in there. So that's what's happening here. So carbon is sp2 hybridized, 120 degrees. Then carbon becomes sp3 hybridized. It becomes tetrahedral. It has an angle of 109.5, and then it returns back to its original shape, which is sp2 hybridized. Again, it's 120 degrees, and it's trigonal planar. So did we use the word when we were answering this? Did we use the word trigonal planar? That should have been used. So where's the question? Coming back to the question, I think we did use that. Now the next part of the question is: you clear? Is that clear, Munia? Sound clear? Bhasgar, is this clear?
Yes, sir.
So now the next part of the question is when naphthalene undergoes nitration, a mixture of 2 organic products are formed. Each compound contains 1 nitro group. Suggests the structures of these compounds. So he's saying each one would contain 1 NO2 group. So he says undergoes nitration, a mixture of 2 organic compounds is formed. So it's a mixture of 2 organic compounds. So what could be those groups? And he's saying undergoes a mixture of two organic compounds is formed. Each compound contains one nitro group. One nitro group. So each compound. So the entire thing will have basically what he means is that the entire thing should have one NO2 group. So you've got only two options. Either the NO2 group will get attached at this position. So that's one of them. Or the second option is
4.
now all these positions are exactly the same. So either the NO2 groups gets attached to this position. Now these positions would be exactly the same. Like if it gets attached on this position, it's just a flipped around version of the same molecule that we did earlier. Or if it gets attached to this position, right? Then even in that case, it's a flipped around version of the same molecule. Or it gets attached to this position, right? So all these positions are kind of the same positions. Is that clear? I mean, this position,
Yes, sir.
this position, this position, and this position. Like if you attach an NO2 group, one NO2 group, remember, there's only one NO2 group that's getting attached. So all of these positions would be kind of exactly the same. So that's, so let me just quickly draw one of them. So we're drawing the first one. So that's one. And what's the other one? The other one is this one. So the other one
Yes.
is this one. Now these positions are exactly the same. You put an NO2 over here, or you put it on top over here. They're kind of flipped around versions of each other. Or you put it over here, or you put it over here. They're exactly the same positions. Is that clear?
Yes, sir.
ठीक है, sign clear है? Ibrar, is this clear? Bhaskar?
Yes, sir.
Achha, so the others are just flipped around versions of each other. So the next thing is naphthalene can be oxidized under certain conditions to phthalic anhydride, whatever this is. Construct an equation for this reaction. Use O to represent an atom of oxygen from the oxidizing agent. So the first thing is construct an equation. What is getting oxidized? It's naphthalene. Now, a lot of questions are similar to this. What they do in a lot of questions is they are always checking whether you know how many hydrogens and how many carbons you've got. So can you tell me how many carbon atoms and hydrogen atoms are in naphthalene? Because if I don't know how many carbons and hydrogens are there, I won't be able to make the equation. So how many carbons are there? That's 1, 2, 3, 4, 5, 8,
10.
10. So there are 10 carbons, right? Now the tricky part is how many hydrogens does it have? Now to count the hydrogens, you got to remember the structure. Where's the structure of benzene? This one. Remember, carbon in benzene only makes 3 bonds. So if you see it only makes 3 bonds. There is no fourth bond. Carbon is sp2 hybridized. It's only making 3 bonds. The fourth electron is delocalized. It's not bonding. So if I go back to the question, this carbon at the moment is making 2 bonds. So there should be 1 H with this. This one also is making 2 bonds. So there should be 1 H with this. This carbon atom would also be having 1 H. This carbon atom would be having 1 H. Would there be any hydrogens with this one?
No, sir.
Okay, because
No.
it's already making 3 bonds. This is also already making 3 bonds. So this is something that they were checking. I mean, they weren't really interested in your equation. They were basically more interested in the fact, okay, are you able to figure out what this is? So the middle carbon atoms, these ones, they would not be bonded to hydrogens because they're already making 3 bonds. So it's going to be C10 and H kitne ho gaye? That's 4 and 4, that's 8, right? So it's C10 H8. And he said use O as an oxidizing agent. And he told us the product. The product that was getting formed was, what was the product? C8H4O3, C8, C8, and H4 and O3, right? So that's their product. Now that's a weird product. And carbon dioxide and water. Sorry, there's carbon dioxide and water as well. So that balances things out. So there's carbon dioxide and there is There's water. Now that makes sense. So there's going to be 2 carbon dioxides, right? So you probably have 2 carbon dioxides. And not sure hydrogens. How many hydrogens do you have? That's 4 over here. So there should be 8. So there should be 2 water molecules as well, right? So the carbons and hydrogens are balanced. 8 plus 2, that's 10, and 8 hydrogens. So that's 4 and 4, that's fine. So oxygens, how many oxygens total? You've got 3 over here and 2 over here and 2 over here as well. That's 4 plus 3, 7 oxygens. So this would be 3.5 O2 or 7 over 2 O2, right? Is that clear? Is this clear? Okay, they pretty much gave you everything there was in the equation. They gave us the products. As the next one is, so that's 1 mark. This is 1 mark. The next one is deduce the type of reaction shown by this equation. So what's going on over here? You've got a phenol. And what exactly is the phenol doing? What now the question is about the type of reaction. So the first thing is, what is the type of reaction when 2 molecules join up and 1 small molecule is produced? What is the type when there's a water molecule getting produced?
Condensation.
So it's a condensation reaction. So for this, I would have to check the market scheme at the end. But also remember that types of reactions, whenever they talk about the types of reaction, what they basically use the term addition. So you either have, so whenever they use the term, maybe they'll give you mark for condensation, but generally when you have a type of reaction question, it's addition, substitution, or there's a third one which is elimination. So that one is elimination. So you basically have 3 types of reactions. You've got addition, substitution, elimination, and there could be a combination of 2 things as well. Now this is clearly an addition, but at the same time, it's also looking like an elimination reaction as well. That it's just once. So it's an addition plus elimination, because a small molecule is getting eliminated as well. Okay. But let's think of this because we haven't studied anything that's similar to this. Let's try and match it with the reactions that we have studied we have already studied. Because we have studied phenols, we've studied the types of reactions for phenols. So let's try and the reason I'm calling it an addition elimination is that things are getting added. The 2 molecules and 1 molecule, they all got added together. And there was this one tiny molecule that was getting eliminated. But let's use reference because this reaction is totally out of course. It's not in our syllabus. So we have to sort of make something up. So I'm going to refer to the reactions of phenols. Now I know phenols undergo electrophilic substitution. So if you go back to phenols, then you would notice that that there was 2,4 directing groups. We talked about phenols. We talked about the fact that when you have a phenol, the benzene ring is highly activated. What that means is, so what that highly activated benzene means, just a second. So this one. So when you have a sorry. So this one. Just hold on a second. So when you have a phenol, the benzene is highly activated. The lone pairs on oxygen are overlapping with benzene's electron cloud, and the electron cloud is no longer evenly distributed. It's got a higher electron density, a higher charge density at positions 2 and 4 and 6. So the electrophile is most likely going to be attached to positions 2, 4, and 6 because of the lone pair effect. Lone pairs overlapping with benzene. Now the thing is, what reactions did we study? We studied this thing. We studied that, I mean, this one, the one that's shown over here, that positive bromines are going to get attracted to the benzene electron cloud because the electron cloud has a very high charge density and there's going to be a lot of attraction. So the NO2 plus one would also get attached, similar to the one that we just studied. The NO2 will also get attached to positions 2, 4, and 6, the NO2 plus one. So is there electrophilic substitution that's happening over here? Because this is something that we have already studied for phenols. So if I go back to this molecule, let's think about this in a bit more detail and let's try and compare it with the reactions that we've already done. Phenol has lone pairs. These lone pairs, they mix up with the electron cloud and the electron density becomes higher at positions 2. The rest of the electrons, they get repelled. So the electron density is higher at position number 4 and also at position number 6. So if you have a phenol, is there anything that's positive in this molecule? Like if you look carefully, this carbon over here has a very strong, it's got a very strong positive charge. Why? Because it's bonded to an oxygen. So it's a highly polar bond. So what should happen is that the benzene electrons will get attracted to this. They are going to get attracted to this carbon, which is positive. So these electrons are going to get attracted to the carbon that's positive. And that, I think, is exactly what's happening. You can see phenols. I mean, if you think of this in a lot more detail, this is exactly what probably went over here. There was a carbon which was having double bonds. I said there was a carbon that was having double bonds. And that positive carbon, I said this particular positive carbon, this is the one. So it's exactly like an electrophilic substitution. Is that idea clear, that the carbon which is positive over here is getting attracted to the electron density in the benzene and it's bonding to it? Is that clear?
Ji, sir.
Achha, so and again, because it's a reaction that you haven't studied, so we would have to check the market scheme. Is it an electrophilic substitution? Because it looks like from phenol's point of view, it looks like an electrophilic substitution. There used to be an H over here, and now you've got it substituted by something that is positive. So let's have a look. What are the answers? This is 9701S20. I mean, this is one of the latest.
So इसमें oxygen को remove किया गया ना, and the entire phenol has been added to that.
हाँ, एक सेकंड मैं उस पे आता हूँ. क्या कह रहे हो आप कि what is happening here?
Okay, the oxygen has been removed and the entire phenol structure has been added.
हाँ, basically something like this would have happened. Okay, it's something like, if I know it's probably a reaction of phenols. Let's go back to phenols. Where's the mechanism? Just a second. Just 1 second. So no, this is stuck. Sorry. Achha, see, this is what we have studied. Okay, it's electrophilic substitution and bromination. So the positive bromine gets attracted and the negative bromine gets repelled, right? So the negative bromine leaves. So something probably similar is happening over here as well. Like if you look carefully, the positive carbon will get attracted to the benzene electron cloud, and because of the benzene electron cloud moving towards it, the negative oxygen would probably leave. Ibra, is this clear?
Yes, sir.
Achha, but anyways, because this is more of a guess question, you just have to sort of make up the mechanism. Let's just look at the marking scheme and see what answers. Did he accept electrophilic substitution? So which question is this? Is this the right paper? Just a second, 2020. Yep. So this question is 42. I mean, what's the question number? Just a second. So anyways, it must be a question right at the start. Let me just find it. So it's okay. They didn't go for electrophilic. I mean, the first two were actually acceptable: condensation and addition elimination. They accepted that. They didn't go with the third one, which I think made sense. The third one also probably made sense. But addition, elimination, or condensation, those were the two terms that were accepted. Okay, is that clear? Not sure why they left out just 1 second. So we did get the first two right, not the third one. Okay, is that clear? But the third one made a lot of sense. It is electrophilic substitution. It's an electrophilic reaction. A positive carbon atom getting attracted to the two electrons in the benzene. So that is electrophilic, and it's substituting the hydrogen over there. So I'm pretty sure it is an electrophilic substitution. I think they just didn't give it an option. Maybe they were accepting that. Okay, but are these two clear?
Yes, sir.
Okay.
Yeah, sure.
And okay, that's fine. But I think I'm pretty sure that they would be giving third marks. The marking schemes are not very comprehensive. The third one is also probably making a lot of sense. And sometimes, what happens is that sometimes the perspective matters, right? For example, you know that alkenes undergo electrophilic addition, right? Like you have a bromine molecule coming in. So you have a bromine molecule coming in. You've studied this reaction in AS as well. So the perspective is really important. Like whose point of view are you discussing? So alkenes. For alkenes, this is an electrophile. I mean, this is a positive. Sorry, I got this wrong. So remember, when you're discussing the type of reaction, the perspective matters. So from the point of view of the alkene, this is an electrophile, right? And the electrons are getting attracted to the electrophile. Is that clear? So you call it an electrophilic addition reaction. But from the point of view of the bromine, what is this alkene? Is it a nucleophile or is it who gets attracted to positive things?
Nucleophile.
So
Electrophile.
Nucleophiles get attracted to positive things. So basically, the bromine is the electrophile and the alkene itself is the nucleophile. It's always a reaction between a nucleophile and an electrophile. Whenever you have an electrophile, whenever you use the term electrophilic, right? Substitution. The other one is basically behaving as a nucleophile. Is that point clear? So you could have called it a nucleophilic addition as well. But the perspective matters. When you name the mechanism, you're basically naming it from the point of view of the organic molecule. But anyways, we got this right. Anyways, we got two of the options right. The third one wasn't given in the marking scheme. Now the next one is name the functional groups in addition to the benzene ring present in phenolphthalein molecule. Where's phenolphthalein? In addition to benzene, where's phenolphthalein? I think this is phenolphthalein. So what other functional groups apart from benzene are present? What is this functional group? And what is this, obviously? This one is obviously a phenol.
No.
What's the top one? What's this one? What's this one? That one is, when you have serial bond O and O in the middle of a chain, that's an ester functional group. Is that clear? Okay, so that's an ester functional group. And those are the only ones. So name the functional groups, we did that. And then he says phenolphthalein can react separately with two reagents shown in the table, complete the table. So he's talking about excess NOH and excess PR2. So you just have to write what the products are. And you also have to tell them the type of reaction. So excess NOH. So the first one is excess NOH, this one, phenolphthalein, reacting with, did he heat it or not? Is it hot? Just 1 second. An excess of hot NaOH. Now that's, so when you have an excess of hot NaOH, remember esters will break down. An ester will undergo alkaline hydrolysis. So first one, if you react this thing, this phenolphthalein molecule, this entire big molecule over here, if you react it with hot NaOH. So remember this, that esters and amides and all these molecules, where's the rest? An amide will undergo hydrolysis if you heat it with dilute acid or dilute alkali. The amide link will break. All the ester links, if you have any ester link, they're also going to break. So anyways, the board is stuck. So all the esters and all the amides would break. And what will happen if the link breaks? This will turn back into an alcohol and that will turn back into a carboxylic acid. That is how esters are formed. And under alkaline hydrolysis, what happens is you don't get a carboxylic acid. What you get instead is a salt of the carboxylic acid. So instead, the carboxylic acid would react with the alkali. So always remember this, whether it's an ester or an amide, these links will break when you heat them with these links over here. They would break if you heat them with a dilute acid or a dilute alkali. One of the part will turn into an alcohol back again. The other part will turn into a carboxylic acid. So remember this. And under alkaline hydrolysis, the carboxylic acid will react. So that is one thing. This ester link will break. The other part is NaOH is a base. Phenols are acidic. We did the reactions of phenols earlier as well. So this is where's the acid part? This one. So we did the comparison of acids and bases. Alcohols were terrible acids. Phenols were slightly better acids. Phenols would undergo reactions with Na. They would also undergo reactions with NaOH. But phenols were not very good acids, so they would not react with weak bases like carbonates and ammonia. Carboxylic acids, on the other hand, were perfect acids. They would react with pretty much all bases, all sorts of strong and weak bases. So phenols would undergo, but they would react with NaOH. And what will happen if a phenol would react with NaOH? This, I'll show it over here. So the OH group is going to undergo a reaction. It will form a salt. And this one would also undergo a reaction. It will form O-1 and Na+1 would be formed. So remember, phenols are kind of the ones that are somewhere in the middle. So anyways, next one. What's the next question? He was also talking about the reaction with bromine. I said with the first one. Is this clear? You clear? I said now coming back to the next one. That was with Br2 aqueous. So we did the bromination part. We did the fact that when you heat a phenol with Br2, phenols are extremely reactive, and Brs will get added to positions 2, 4, and 6. So Br will get added over here, and Br will get added at this position as well. So phenols are extremely reactive. The electron densities, why were the electron densities higher? Because the lone pair had mixed up and the electron density was really high. So the bromine would have a vigorous reaction. This same thing. The bromine will undergo a vigorous reaction. So phenols are going to be extremely reactive. And the Br will get attached at all positions because of the highly activated. No catalyst would even be required for this. So that's the reaction in this particular case. So I'll move on. So that's the product for this one. The ester group will obviously not react with Br2 aqueous. This benzene will not react because you would need a catalyst. Phenols, you don't need a catalyst. With normal benzenes, you need a catalyst of FeBr3. So this benzene is not going to take part. So now moving on. And the type of reaction. On the benzene ring, that's electrophilic substitution. And the other one, the NaOH one, it was either a hydrolysis of the ester link. I mean, you had to complete the molecule. The one that we drew earlier, you had to redraw this over here. So it was either hydrolysis because the ester was breaking up, or the phenol was reacting. So it was an acid-base reaction or a neutralization reaction, the one that we did with NaOH. So moving on, it's this one is about, I mean, let's ignore that for now. Let's talk about this one. He's saying on the structure of methyl orange, circle the bond or bonds that make this compound a dye. So we did dye stuff. And in dye stuff, somewhere at the end, before this one. So we did dye stuff. We did this thing that an azo dye is something that has this N double bond N azo group between two benzene groups. One of the benzenes is activated. So it's a very stable dye. So we did this. So he's saying circle the group or bond that makes this compound a dye. So it's this thing over here. Okay, that's the thing that's making it a dye. That's the azo group. And he's saying the color of this indicator changes between pH 3.2 and pH 3.4. Assume that the structure of methyl orange at pH 3 group is unreactive. So as it suggests the structure of the methyl orange at pH 3. So at pH 3, this is acidic, right?
Yes.
So that means there's a lot of H+1 ions around. So the question now is, what will those H+1 do? And remember, we did comparison of bases. We did the comparison of bases. We talked about strong bases and weak bases. Somewhere over here, right after acids, we did the comparison of bases. I told you that when you have a lot of H+1, this is pH 3. Remember, pH 3 is acidic. So there's a lot of H+1 around. I told you nitrogen compounds are like good bases. They've got lone pairs. And those lone pairs can accept H+1, except for the amide. The amide is not able to do that. And the reason the amide is not able to do that is that the lone pair is not there. The lone pair mixes up with the oxygen, double bond, and it's not available. So it's not basic. It's not able to attract the H+1. This one attracts H+1 very weakly. Why? Because even here, the lone pair mixes with the benzene electron cloud. So the lone pair is just partially there, not completely there. Over here, the electron density is, in the last one, the electron density is like really high. And the reason is that you've got an alkyl chain. And the alkyl chain is kind of, so the alkyl chain is kind of really reactive. It has an electron donating effect. The lone pair charge density increases and it attracts the H+1 very strongly. So the question now is, you've got nitrogens over here, and he's already told us that it's, so you got this lone pair over here. So the first thing is this would form a dative bond. It will attract an H+1 ion. Then there's a lone pair on this end as well. So it would also attract an H+1 as well. So is that clear? So these N lone pairs will attract H+1 and the H+1 would go and attach to those lone pairs. So these are basic structures. Is that clear?
Yes, sir.
So at pH 3, that's going to be the structure. And then he says methyl orange can be synthesized as shown. So you're starting with NO2. So let's go back to how the dyes were formed. Where's the dye stuff? 1 second. Just 1 second. Let's open the. No, it's still stuck. 1 second. So dye stuff. Now the first thing is, if you want to make it an azo dye, this is the procedure. You start off. I mean, this is the dye that you're trying to make. The first thing is you need to convert it into NH2, and the way you do that is, your starting point is NO2. It should not be NO2. It should be NH2. So the first step is you would have to convert this thing. This is your SO3 -1 Na +1. So the first part is you would have to convert that into NH2. That's reduction. Basically, the oxygen would be lost and the H would be gained. And the reduction of nitrobenzene happens with 10 plus concentrated HCl. So that's the first step for making an azo dye. You need an NH2. And then that NH2 is turned into an N triple bond N +1, which is a disonium ion. It's a highly unstable disonium ion. And you can do that by using NNO2 plus HCl, and the temperature's got to be less than 10. So that's the next step. The next step is this NH2 needs to be turned into N triple bond. It should be turned into an N triple bond N. +1, the other thing remains exactly the same. And to do that, that would require NaNO2 plus HCl. And the temperature's got to be less than 10. It should be around 5 degrees centigrade. So it's a very unstable disonium ion. And this one is a very strong electrophile. So it's going to immediately get attracted to the benzene electron cloud next door. And the end result would be that a diazo group would be formed in the middle. The electrons from this benzene will start bonding with the N triple bond N, and they would end up forming this azo dye. So that's the whole process. Remember, azo groups are really important. You get a lot of questions on these pretty much in all papers. This is an azo dye. It's a very stable dye. Dye has got to be extremely stable because paint has to endure a lot of things. So you don't want car paint to turn into some other color like after 1 month. So paints have to be extremely stable, and azo groups are really stable. So you start off with NH2, that's your starting material. You turn it into N triple bond N +1, which is a highly unstable compound. If the temperature goes above 10 degrees centigrade, it will decompose immediately into a phenol. So that's the first step. A highly unstable disonium ion is produced under these conditions. And then that highly unstable disonium ion is reacted with an activated benzene. Why should it be activated? Because only then the electron density would be high at positions 2, 4, and 6. And therefore it will be attracted to the N triple bond N +1, and they would end up forming an azo dye. I mean, this benzene should be slightly higher. I said, but anyways, that's something you should remember. TK, you have the notes, make sure you remember this. So deduce the compound, you have to, the conditions in this reaction are NaOH aqueous. Alkaline conditions are used. The previous conditions are already mentioned. So we've pretty much answered most of the stuff. The next one is about, is the previous one clear? Is this clear? Sign clear, Ibrahim, Munia, is this clear?
Yes, sir. Thank you.
Let's do another one. Now you have this molecule over here. He's saying that, what he's saying is that benzophenone can be synthesized from benzoic acid in 2 steps as shown in step 1. So you want to make this thing. So basically, he's saying that step 1 compound J, a reactive intermediate. So there is this thing over here is a reactive intermediate that is formed. And it then reacts with an organic compound to form this thing. So I need to look up the reactions. Like, we did a lot of electrophilic substitution reactions. So this needs to be looked at. We did a lot of electrophilic substitution. Right at the end, we also did alkylation and acylation. The very last part. So if you look over here, you would notice that they're attaching a C double bond O group to benzene. This happens when you have a benzene and there's a C double bond OCl, an acyl chloride. The carbon has a very strong positive charge. So that's acylation. Like if you have a carbon chain and you have an acyl chloride, which is C double bond OCl, the positive carbon is going to get attached to the benzene. So the carbon chain the positive carbon in double bond O is going to get attached to benzene, and the Cl would eventually leave. So in this reaction, if you look at this reaction, and where's the reaction? So you'll notice that there's a C double bond O. So the other molecule I'm suspecting is just a normal benzene. It's a normal benzene. This one over here, this molecule over here, has first turned into an acyl chloride. The carboxylic acid can be easily turned into an acyl chloride. This carbon gets a positive charge, so it's going to be very attracted to this, to the electron cloud from the neighboring benzene. That's how you're going to get C double bond O in the middle. The Cl would eventually leave.
Makes sense.
So he was basically talking about this is basically acylation. I mean, because he was using AlCl3 catalyst. And if you look at AlCl3, that would have given you some hint that this must have been electrophilic substitution. I mean, the closest, although this was kind of really hard to actually predict, but the AlCl3 was the one that gave you some hint about what type of reaction is happening. It must be electrophilic substitution that's going on. And the C double bond O is getting attached to a benzene. So it's an acylation reaction, so this carboxylic acid first turn into C double bond OCl. How do you remove the OH and turn it into Cl? You react it with PCl3 plus heat, or with SOCl2, or with PCl5 as well. So chlorination happened for carboxylic acid. It turned into C double bond OCl. That is very reactive. We did the hydrolysis. It's a very reactive substance because the carbon has a very strong positive charge, and the benzene is going to get attracted to this positive carbon atom, and this would give you this. So we did answer everything. So I deduced the identities. We did do that, and suggest the reagents and conditions for step 1. We did that as well. And then you have this reaction. Now this one is also a lot of guesswork, actually. Like, you're given this molecule and they're saying that an oxidation reaction is happening because it's KMnO4. So there is an oxidation that's happening, that's taking place. And they're saying that this molecule, C13H12. So what could be C13H12? That's the question. So you need to go back. C13 means that there must be 2 benzenes. But one benzene has 6 carbon atoms, the other benzene has 6 carbon atoms. So that means there must be another carbon atom somewhere in the middle. And I mean, there is, we saw that there is a carbon in the middle, right? But there is no oxygen now. He's saying there are 12 hydrogens. So that's 1H, that's 1H, 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 1H. So that's 5 hydrogens. This is 5 hydrogens. So that's a total of 10 hydrogens. That means there are 2 hydrogens left. So this carbon would probably have 2 hydrogens. That's the only possibility because the only thing that's the oxygen is not there because the formula doesn't have oxygen. So that's the only possibility that you have. Is that clear?
Yes, sir.
And they didn't ask for any conditions. They just asked you to deduce the identity of compound L, and you were able to do that without any prior knowledge of anything. You just figured out that this is C13H12, so it must be something similar to this. It's got 13 carbon atoms, so that's 2 benzenes. But that would give you 10 hydrogens. So the 13th carbon would probably have the 2 hydrogens, and that's it. And then he's saying, name the mechanism of step 3 and suggest the reagents and conditions for step 3. So the question now is, what's going on over here? Step 3, what happened? What happened at step 3? So that's the question. Now step 3, what type of compound is this? This is probably a halogenoalkane. And this reaction is also very similar to alkylation now. I'm going to refer to the alkylation just shortly. The carbon here is positive. The bromine here is slightly negative. And there's another benzene coming in. So there must be another benzene. The benzene has an electron cloud. And the electron cloud would be attracted to this particular positive carbon atom. This is alkylation, just like acylation. Right before that, there was another reaction which was alkylation. That if a carbon has a halogen, the carbon would be positive, and that particular carbon atom will get attracted. The positive carbon atom will get attracted to the benzene electron cloud, and that carbon will go and bond with it. So this carbon goes and bonds with this benzene. So any carbon that has a halogen attached to it will be positive, and it will go and attach itself to the benzene electron cloud. So that's alkylation. So you've got 2 reactions: alkylation, where a normal carbon chain gets attached to benzene. The other one was acylation. We just did acylation as well. In acylation, again, a carbon chain gets attached to it, but it's a acetyl bond O that gets attached to it. So they're both kind of similar reactions. In this one, in this specific case, this one looks like an alkylation reaction. You have a carbon chain and the carbon has a positive charge. Why? Because it's bonded to bromine. And that positive carbon atom is going to get attracted to benzene. So the catalyst that you're going to use for this is FeBr3. So it's an alkylation reaction. So this carbon goes, the bromine goes away, and the carbon goes and bonds with the next benzene. Is that clear? Munia, is this clear?
Yes, sir.
So let's continue next time. I'll just try and organize the notes a bit more. They're just hanging up on me. Just wanted to refer to the notes a lot more. I'll share the notes again, okay? So go through the notes, organic notes. We'll just practice these a lot more, a few more questions, because these are really important, okay? You get a lot of 30 marks questions on organic chemistry. So make sure you revise those notes, and I'll send you some more organized notes, okay? Let's continue next time.
Sir, where can I get the recorded?
Yes, I sent. I'll share a link again.
But it's telling me to register with my Gmail account.
On the website?
Yeah, when I tried to access it, it was saying that I need to register with my Gmail account.
Instead, there's this other one which I sent. What I'll try and do is I'll remind me again on WhatsApp.
Okay, sir.
But do remind me again, like in 2 hours, and I'll share the video lectures, all of them.
Okay, sir.
Okay, then take care.
Okay, thank you so much for today. Okay, bye.